So welcome everybody to this seminar organised by the East Anglia branch of the Institute of Physics. Thank you for joining today. Just a little bit before we start, just want to let everybody know that we will be recording today's session, today's questions. So if you ask a question or anything, that just so you're aware of that. And if anybody would like the captions during the seminar, then you can turn them on yourself at the bottom of the screen. They should just appear automatically then at the bottom. So today we have Tim Rawle with us. He's from the European Space Astronomy Centre, and he's going to talk today about exploring exoplanet atmospheres in the age of the Webb and Ariel. So Tim attended Durham University, completing his MSci in Physics and Astronomy, and then going on to do a PhD in observational astrophysics. He then moved to the Steward Observatory at the University of Arizona in the USA, where as a postdoctoral scholar, he studied far infrared gravitational lensing using the newly launched Herschel Space Observatory. Tim then moved to work at the European Space Agency, first as a research fellow, embedded at the Herschel Science Operations Center in Madrid, and then later as an instrument scientist for the European contributed NIRSpec on the Webb Space Telescope. In 2023, Tim returned to the ESA as operations and archive scientist for the upcoming Ariel exoplanet mission, which is due to launch in 2029. And so thank you, Tim, for speaking today, and I'll hand over to you.
Thank you very much, Christina, and hello to everybody. Yes, today I'm going to be talking to you about the exoplanet atmospheres, particularly as observed by Webb and in the future Ariel too. So not to repeat anything, but I'm Tim Rawle. I work for European Space Agency in Madrid as an operations and archive scientist for the Ariel mission. Previously, I was indeed based at the Webb Operations Center at Space Telescope Science Institute in Baltimore, Maryland, as an instrument scientist for ESA's NIRSpec. So I intend to showcase highlights of recent exoplanet observations by Webb and also give an overview for the Ariel mission and science objectives. But first, I'd like to give a brief introduction to extrasolar planets themselves. Until very recently, the only planets we knew for sure existed were in our own solar system. There were 9 of them: our Earth, the classical Mercury, Venus, Mars, Jupiter, and Saturn, and then also Uranus, Neptune, and Pluto discovered in the 1700s to 1900s. It is worth noting, though, that after the IAU classification of Pluto and Ceres as dwarf planets, we should now really say that there were 8 or maybe 10 planets in 1990. But I'll stick with just 9 planets in 1990. The first evidence of an extrasolar planet was arguably in 1917. It was hiding in the spectrum from a Mount Wilson 60-inch observation, but no one knew it until a century later. It was observing the Van Maanen white dwarf, which is a remnant of a sun-like star, and there was a calcium absorption line seen here in the image that's being blown up from the spectra. This is the original plate image from that spectrum. And those lines seen here are heavy elements that must be due to pollution of that star by external debris. So this is evidence for presence of planetary debris and past exoplanets in that system. However, the first really confirmed detection of an exoplanet came in 1992. And this was from the embedded signal of not 1, but 2 planets in the otherwise regular variations of a pulsar. In fact, a third planet was discovered around the same pulsar in 1994, a year later, or a couple of years later. Then the next year, in 1995, we come to the first, what we would consider the real proper first exoplanet, confirmed around a main sequence star like our Sun, Pegasus, or 51 Pegasus, which is 50 light years away from Earth. The planet, 51 Pegasus b, as shown on the right here, is a gas giant. It's a little larger than Jupiter, but significantly closer to the star than our Mercury is to the Sun. This type of exoplanet is known as a hot Jupiter and would become a dominant type discovered in the early days of exoplanet hunting. It's interesting as it has no analog in our own solar system. Now, fast forwarding to today, we have now confirmed almost 6,000 exoplanets. This diagram on the left shows artist impressions for many based on the known size and density of these planets, whether it be gas giants or more Earth-like terrestrial planets. And these exoplanets do exhibit a diverse range of characteristics, from many more hot Jupiters, as well as super-Earths, these are rocky worlds, but also sub-Neptunes that could either be large terrestrial worlds with thick atmospheres or small gaseous planets. Almost 1,000 systems with more than one planet has also been discovered. And we likely have further planets that have gone undetected so far. And that goes the same for the systems that we currently only know one planet for as well. They could also have many other planets. We also have no reason to believe that most stars will not have multiple planets. Now, one of the most famous multiple planet systems is TRAPPIST-1. At first glance, the figure on the left is much like our inner solar system, albeit with 7 terrestrial planets instead of our 4. But notice the scale. It's blown up 25 times, and the entire system is much smaller than the orbit of Mercury. However, because the star is very small and cool, it's an ultra-cool red dwarf. That means that the illumination radiation on the planets is much lower. And the figure on the right shows that illumination as relative to the Earth. And also on the y-axis, it plots against the planet density. So at least 3 of the planets in this TRAPPIST system, 3 of those rocky planets, are in the notional habitable zone. That means the illumination is similar to we have on Earth, and the density of the planet is similar to we have to Earth as well. Notice, however, that Mars is also in the habitable regime according to these parameters. It's still interesting that 3 of these TRAPPIST planets could be habitable. We can actually now compile a significant number of terrestrial planets in the notional habitable zone around their own stars. On this figure, Earth is right at the top. The TRAPPIST-1 system is at the bottom, showing those 3 planets, D, E, and F. And then there is a whole range of other planets that are in their habitable zone. The images here, again, are artist impressions, obviously not real planet observations, but the sizes are relative to the real size of those planets. So we have a lot of planets that we now know of, which do lie within this terrestrial and habitable zone. But taking a step back to the evolution of planets, every planetary system is one outcome of a process with many possible outcomes. The solar system is the most familiar outcome for us, but we do not yet know if that is truly normal or simply an outlier. We need a large, diverse sample to understand planets in general. Density is a primary key to unlock the composition of planets, distinguishing between interiors that are largely gaseous and those with a surface, whether that surface is rock or a liquid. So here we can see artistic renderings of a number of non-exhaustive set of interior models. These could be roughly discriminated by considering the bulk density of the planets, simply calculated with a knowledge of a planet mass and radius. And in this set, we have a wide range of things. We have a very solar system-like planet with a molten core, then rocky mantle, and maybe a water ocean. There are planets with subsurface oceans, and then also water vapor, water-rich worlds, as well as gas giants such as Neptune and Jupiter as well. So we have a lot of models for the interior of planets. What we really want to do is link those models with the observations we see to really try and characterize the planets that we're discovering. However, only a small fraction, fewer than about 5% of the planets that we've discovered actually have both a size and mass estimate, which we need for a bulk density assessment and then comparison with those planetary models. Now, the ESA and Swiss CHEOPS mission, which has been operating low Earth orbit since 2019, is busy providing many more precise radius measurements. And in the future, ESO's Plato mission, which is due to launch in 2026, will continue this work at a higher precision. But what we'd really like to know, even more than the pure density, is the fraction of planets with is the fraction of planets with any of those interiors. And for that, we really need spectral data as well. And the bottom line is we just do not know a lot about the planets we've found yet because we don't have anything other than a mass and a radius. So next, I'd just like to take a step back in time a little bit and give a brief overview of the methods used to discover these exoplanets. The laws of physics dictate that a star and a companion planet orbit a system barycenter. If a companion planet is large enough and or close enough to the star, the motion of the star around the barycenter is perceptible as a wobble to the straight path of the star around the galaxy. This little wobble can be seen as the ribbon shape on the diagram on the left, and that's how we would observe a star moving over time. Now, this method was used a lot in the early days of exoplanet discovery, and it's heavily biased towards hot Jupiters, which are large and close to their star. The radial velocity method also uses the corresponding reaction of the star to the presence of a planet. This time, we watch for the Doppler shift effect in a stellar spectrum over time, caused by the star moving along our line of sight due to the orbital motion of its planet. For this method, the system must be relatively edge-on because we need the star to move either towards us or away from us. And it is, again, biased towards larger stellar motions, and therefore it's biased towards larger and closer planetary companions. Direct imaging is generally very difficult as the stars are bright while the planets are very faint and generally very close to their bright planet. Specially designed coronographs try to block the central starlight, either via a physical occulter within the instrument's internal light path, or a 4-quadrant phase mask, which ensures destructive interference of the light from the central source. Extraction of a planetary signal in both cases is still often very tricky. This is complementary to the two previous methods, though, as it is far easier for planets that are large orbital radius to be detected. However, still larger planets are easier to detect than smaller planets, just because they reflect more of their sun's light generally. Although that is also a function of the composition of the planet, so a very small icy planet might be easy to detect. And a fourth method is microlensing, which exploits the gravitational lensing effect of a foreground star magnifying a background star. If a foreground star has a planet, it can appear as a variation observed in the brightness of the magnified background star. This method is also biased towards large planets, and is also not a controllable observation, as repeat observations are pretty unlikely as a foreground star of interest has to pass in front of another star. However, with large and wide area surveys, you can get lucky and discover exoplanets by this effect, but not really useful for following them up. Finally, the transit method relies on the dip in luminosity of a star as a planet passes in front of it. It relies on a system being relatively edge-on, and with larger and closer planets again being easier to detect. Both Cheops and Plato use this method to estimate the radius of a planet by monitoring the magnitude of a decrease in the brightness through the transit, especially as a planet passes the limb, which is the darker outer edge of a star. Now, an important extension to the transit method is observation of a full phase curve, as well as the transit, which is the primary eclipse, which is when the planet passes in front of a star. There is also a dip in brightness during the secondary eclipse. That's seen as an increase in brightness shown in the center of the light curve figure here on the left. Oh, sorry, in the center. As the planet gradually moves around the star, on the left-hand side of a star, as it moves towards us, it's going from showing us the day side to the night side, and then on the far side of a star, as it is now, it's going from a night side to a day side. And these gradual differentiations in that brightness can be picked up, especially as it abruptly disappears when it goes behind the star in the secondary eclipse. Observing these full phase curves is time consuming, though. You obviously have to wait for the planet to do a full orbit of its sun. Now, for very close by, like hot Jupiters, that can only be a matter of a couple of days or less. But even so, that's quite a lot of time to spend on one telescope. And unless you have a very stable, high precision telescope to see the small day-night difference, you gain little when the planet is not really in the primary eclipse. On top of the fact that we're actually very good at predicting the timing of future transits from orbital parameters, it means that phase curves hasn't yet been a tool that we've used a lot. We tend to just target the exact primary eclipse time when we know it will happen and just observe that with a little bit of extension each side, so we get a baseline of the star without the planet in it. Now, not only can we observe the transit, but during the transit, starlight is not simply blocked by the planet, but it'll also pass through the upper layers of the atmosphere, where some light may be absorbed, imprinting the composition of the atmosphere onto the stellar spectrum. Using wide-ranging sets of atmospheric models, the imprint can then be inverted into constraints on the atmosphere, a process known in the exoplanet field as retrieval. Now, although most absorption occurs in the upper layers of the atmosphere, we can actually get down to the lower levels with enough precision in the detection signal. So it's a matter of having a bright enough star and a sensitive enough telescope. The figure on the upper right here shows the estimated signal of 3 planets in our own solar system as if we were observing them as a transit observation. So Mars, Earth, and Venus. Mars and Venus just show absorption, very deep absorption from carbon dioxide. Mars has a very tenuous atmosphere, but it's carbon dioxide mostly, whereas Venus has a very thick CO-rich atmosphere, but again, not a lot else in its atmosphere. Earth, on the other hand, shows that carbon dioxide, but also a big absorption from the ozone layer that we have on the Earth, as well as many features associated with water. And that's what we're really looking for in exoplanet signatures. Now, knowing the composition of the atmosphere as well as the bulk density of a planet can then really help us determine the composition of a whole planet. So going back to 2 of the interior models, these 2 would have the same bulk density. One has a very dense rocky interior, but then very, very low mass primordial atmosphere of hydrogen and helium. Whereas the other planet, same bulk density, but the composition is very different. It has a small rocky core and then a big icy interior covered with the heavier water vapor atmosphere. So same bulk density, but we definitely see a different signature from the atmospheres of these 2 planets. So we can break the degeneracy between the models by knowing something about the atmosphere. Okay, so now we turn to the beautiful James Webb Space Telescope, which is a partnership between the European Space Agency, NASA, and the Canadian Space Agency. And as a NASA person, I should put them in that order. I'm sure NASA would disagree. Webb is located at the Lagrange 2 point, which is 1.5 million kilometers from Earth. That's about 3 to 4 times the distance of the moon. And there are 2 notable features of Webb, and that's the enormous gold-plated mirror, 6.5 meter diameter, optimized for the infrared wavelengths. And then also the tennis court-sized sunshade, which is designed to keep the instrumentation in shadow and therefore as cold as possible, because in the infrared, you don't want any ambient heat escaping and getting into your instrumentation, because infrared is thermal radiation, of course. Over the first 3 years of routine operations, Webb was used to collect spectacular science, and just 6 of quite iconic now, I think, images from Webb are displayed on the bottom left of this slide. None of them are to do with exoplanets. I'm not going to go into any detail, but all of these imaging has actually spawned around 3,000 publications in only 3 years. Now, although it was originally intended to last 10 years, that lifetime estimate was limited by the fuel needed for spacecraft housekeeping and pointing at the correct parts of the sky. The launch on the Ariane 5 rocket on Christmas Day 2021 was so perfect that we actually needed a lot less fuel than estimated during the transit to L2. And consequently, the expectation is now that we have 20 years worth of fuel left. So hopefully the instruments can survive that time, and Webb will last for a long time yet in the future. Now, Webb has a complement of 4 instruments with a range of capabilities, including imaging, coronography, multi-object spectroscopy, and spectral imaging via integral field units, for instance. The US contributed NIRCam, which provides imaging in the near infrared up to 5 microns. NIRCam is the near infrared camera. The ESA European provided near infrared spectrograph, NIRSpec, offers complementary near-IR spectroscopy in multiple modes, including an integral field unit, multi-object spectroscopy, single slit. It's a very powerful, versatile machine. The Canadian NIRS handles telescope guiding, but can also be used as an imager and slitless spectrograph. And finally, the joint US ESA MIRI provides the mid-infrared capabilities of JWST from 5 to 30 microns. For exoplanet science, coronography from NIRCam and MIRI and single object spectroscopy from NIRSpec, NIRIS, and MIRI are the most important modes. Now, one thing we have to say about Webb instruments is that while they can observe in parallel, they do not observe the same region on the sky at the same time. And that means that full wavelength coverage can be very expensive if you want all the way from near infrared to the end of the furthest red we go in mid infrared. So all the way from 1 to 30 micron. It requires multiple observations with a different instrumentation to obtain that. Okay, so going on to some of the science highlights. Before we move on to atmospheres, here is direct imaging via the coronagraphs on Webb. The 4 thumbnails show 4 different imaging bands of the same planet, and the white star marks the location of the star that's been blocked out. So the signal you're seeing in the center of each of the thumbnails is the planet itself. And this is HIP 65426b, which is a super Jupiter lying a little less than 400 light years from Earth. Now it's approximately 90 AU from its star, which is about 3 times the orbital radius of Neptune. So it's a very good target, being very well separated from its star for such a direct imaging observation. And I think it's a beautiful display of the power of James Webb in actually seeing this planet in the mid-infrared as well as the near-infrared. Going on to the atmospheres of exoplanets from Webb, WASP 96b was first discovered in 2013, but Webb has now yielded this beautiful white light curve for the transit. You can see a very high precision light curve showing a slightly curved bottom of the transit and also those sloped wings either side of a transit. This is all emblematic of those sides of the sun where it dims towards the edges of a star, and also the fact that we might even be able to pick out some little signals of star spots if they existed, but this is such a smooth curve. This is a very clean star, probably with no star spots or speculi, which are the dark and light patterns you sometimes see on stars, variable stars particularly. Now on the right here, we see a single time series observation of the same planet. This is actually at the very start of operations of Webb, and it's from NIRS, and it's providing the most detailed IR transmission spectrum ever seen up to that point. The starlight blocked out by the atmosphere is approximately 14,000 parts per million. That's about 1.5%. So it's a very, very precise observation for that time, and certainly the best ever achieved at that time, right at the beginning of the Webb mission. And this is all for a planet lying more than 1,100 light years from Earth. And this spectrum shows evidence for both clouds in the fact that the peaks are actually slightly lower than would be expected from water absorption. And then also from haze, which is shown in a spectral shape at the blue end of this spectrum. That's just symptomatic of the models we see for haze. And there are so many lines of water in the spectrum as well. So it's a very nice example of what we can do with Webb for exoplanet atmospheres. Now, WASP 39b is another hot Jupiter, about 700 light years from Earth. Incidentally, this is one of the only exoplanets to be officially named by the IAU due to the Name ExoWorlds campaign for their 100th anniversary. It's called Boca Prince, which apparently is named after a beach in Aruba. But this NIRSpec prism observation of a planet was again from one single transit observation, no repeating. And it shows exquisite detail, reaching a level of 220 parts per million per spectroscopic bin. It actually contains the first ever detection of both carbon dioxide and sulfur dioxide in an exoplanet atmosphere, and there's substantial water features shown as well. So it's another amazing demonstration of what we can do with a different Webb instrument as well. Now return to TRAPPIST-1 system, and in particular the Venus-like TRAPPIST-1c. As shown by the diagram we saw before, TRAPPIST-1c is very Venus-like in both illumination and density, so you might expect it to have a hot, dense, carbon dioxide-rich atmosphere like Venus. However, the MIRI observation shows it's not at all like Venus. It rules out CO2-rich atmosphere. Airlessness is possible, but it could also have a water vapor or even oxygen-rich atmosphere. We don't really know. What we do know is it's the coolest rocky exoplanet ever observed. Now, even with Webb, the transit method has a hard time with TRAPPIST-1 in general. And this is due to the large variabilities in the star swamping out the planet signal. You can see this in those wide spread of the blue individual brightness measurements in the plot on the left. We have to really look at the averages, which shows the stability of Webb then to be able to see the transit at all. And actually, this is a more general problem, making precise measurements of the planet-like curves. With variable luminosity due to stellar activity, sunspots and speculi on the surface of the stars, we need very good knowledge of a star for exoplanet exploration. And this makes phase curves look even more advantageous, actually, as it yields a longer baseline. But that's just not possible with Webb, where time is precious and has to be shared between all the different astronomical communities. Days of dedicated stellar calibration observations during the rest of the phase curve is just too difficult to justify. Now, TRAPPIST-1c doesn't seem to have an atmosphere, and this has been a common theme for rocky planets targeted by Webb. However, this plot on the left from a recent review paper shows that the planets targeted are not necessarily expected to have an atmosphere, and that might be a mistake in the selection for targets for Webb, or it might just be that the capabilities of Webb still aren't quite good enough to look at planets that may have atmospheres. So planets should retain their atmosphere if they escape velocity, the x-axis here, outweighs the total energy provided by the star, which here we parameterize by the cumulative XUV radiation on the y-axis. And this all means that planets falling below the shoreline line on this plot, such as Venus and Earth, should have atmospheres, whereas the planets above the line shouldn't. And we can see that actually most Webb targets lie above that line, and then maybe we don't expect them to have atmospheres. So stepping back to a full population of exoplanets, not just those rocky terrestrials, Webb is gathering a large sample comprising many tens via the transit method. However, we can't expect a real increase of the total time dedicated to exoplanet science, as shown in the plot on the right. It's never going to get more than 30% because, well, there's a lot of time that needs to be allocated to stars, galaxies, black holes, and all those other cool, interesting stuff in the universe. So I think Webb will continue to investigate individual objects. It's never going to be a great survey telescope for exoplanets. So for a statistical sample of exoplanets, we really need a dedicated mission. And that's where the atmospheric remote sensing infrared exoplanet large survey comes in, Ariel. Ariel is an ESA mission dedicated to exoplanet atmospheres, and it's supposed to last 6 years, launching in 2029. The prime contractor is Airbus, with a consortium of 60 institutes from 17 ESA member states and additional contributions from NASA, Canadian Space Agency, and the Japanese Space Agency. And while much smaller than Webb, its primary mirror is only about 1.5 meters. The platform is designed to be highly stable. We don't actually need Webb sensitivity, like the huge mirror, to investigate exoplanets via transit spectroscopy, as the host stars are intrinsically bright and point sources. There is no requirement for spatial resolution in this method. We just need the high precision given by a very stable telescope, both structurally and thermally. And Webb's efficiency in observing exoplanets is generally not limited by sensitivity, but rather by the cost of repeated observations to obtain a full infrared wavelength coverage. Ariel will be efficient in covering the full wavelength range from 0.5 micron all the way up to 8 microns in one shot, with all the instruments fed by the same primary beam and beam splitters, which minimizes the need to repeat targets that yield a high signal to noise in the first single transit. And here you can see a little bit more details of the design of Ariel. Now, Ariel is intended to provide the first chemical census of a large, diverse sample of exoplanets, answering questions on exoplanet formation and atmospheric evolution. Ariel will observe more than 1,000 transiting exoplanets, preferentially focused on short periods to optimize the efficiency in the transit observations. Now, we know that planets migrate into the inner regions during formation, and this means that not all short period planets will have actually been originally formed in the inner solar system, but could have actually been delivered from the outer regions by migrating in. And this means that the population will be more diverse than you might expect from just concentrating on short period objects. The figure on this slide shows the dynamic pathways that can deliver planets from their formation regions to the region that Ariel will observe. Early migration acts while planets are still forming, while late migration occurs afterwards. As a result, the two mechanisms, early and late migration, are associated with different compositional signatures of the planets. So we'll also be able to detect with the Ariel data which planets migrated when, or if they were actually originally in the very inner regions of our solar system for their entire life. The Ariel sample is expected to include hot Jupiters and sub-Neptunes, water worlds, as well as large terrestrial planets with clouds and seismic activity. A range of molecular gases and compounds, and also condensed species, all absorb light within the infrared wavelength range covered by Ariel. So there's plenty of different signatures there to be looking for. And the simultaneous wavelength coverage of Ariel enables stellar calibration and the core planetary science to occur at the same time. This is key to being a really efficient, effective survey telescope. The stellar activity and the bulk planet properties, such as cloud and haze coverage, can be tracked via 3-band optical and near-infrared photometry up to 1.1 microns, while the detailed characterization of the chemical composition of the atmosphere is derived from the infrared spectra from 1 to 8 microns. There are many processes involved in the formation and evolution of planets, both stellar in origin as well as more internal to the planet, such as plate tectonics. Ariel will begin to disentangle the impact and relative importance of all of these processes. The Ariel survey strategy involves several tiers, whereby the highest precision, the multi-epoch observations form a smaller benchmark sample of 50 to 100 exoplanets. And then coarser observations fill out the full survey of more than 1,000 planets. Each planet in the main survey will be observed during a transit or a secondary eclipse, whereas the benchmark set includes at least one of each eclipse type and probably many other epochs as well. Now, before Webb, phase curves were not a major aspect of the tiered survey plan for Ariel, but with mounting evidence that stellar activity could be a major contributor to noise and can be more effectively mitigated with long baseline phase curves, the Ariel consortium are now assessing the impact on the survey of including a large number of phase curve observations. So it's not necessarily in this slide now, but it's certainly what may arise in the next book. So the Blue Book of Ariel is going to come out in the next year or so. The Red Book was the last major science publication from the Ariel Consortium. Now, Ariel is due to launch in 2029, and it's actually going to launch together with Comet Interceptor, which is an ESA mission to, as the name suggests, intercept a comet, or more actually, it's going to try and intercept an interloper from outside the solar system, and we just had one, so it's a shame Comet Interceptor wasn't already up there, but I'm sure there'll be plenty more for it to see. So this dual launch on the Ariane 6 is still driven by the the Ariel schedule, though. So once Ariel is ready, we'll go. I think Comet Interceptor is coming along fine and is almost ready as well. So the status of the spacecraft is it's on track, and payload testing should start next year. I'd like to take this opportunity to briefly advertise the Ariel Open Conference in March next year. This will occur at the ESA Conference Centre at EXAT in Harwell, Oxfordshire. That's just opposite the Rutherford Appleton Lab campus. And this should be a great opportunity for anyone in the wider exoplanet community to connect with the Ariel consortium. So the future is bright for ESA's exoplanet exploration. So finally, a brief word on the exoplanet fleet in general. So NASA's Kepler and ESA's Gaia missions have recently ceased operations. Gaia very recently, only in the last few months, although data processing is going to go on for Gaia 4 years. NASA's TESS and ESA's CHAOPS missions are reaching the end of their initial extensions and will hopefully last several more years, yet gathering ever-growing sample of exoplanets with well-constrained mass and radii. Webb is working wonders, demonstrating a wealth of information available on exoplanet atmospheres. And that is our bridge to the next generation of ESA-dedicated exoplanet explorers, which will be Plato, taking over from CHAOPS with higher precision, and then, of course, Ariel, which can really start to perform this census of exoplanet atmospheres. So thank you for your attention, and I'm happy to take any questions.
Thank you very much, Tim. So yeah, now we're over to questions. So if you'd like to put questions in the chat or raise your hand and we will unmute you. So perhaps I'll start with a question. There's a sort of observational bias that we're seeing at the moment in terms of, we've got more hot Jupiters and that sort of thing. Are we starting now, because we've got so many, to sort of understand what we're seeing as a bias and what we're seeing as what we think might be normal? Have we got some ideas on that?
I think we've got some good ideas on what is a bias in our sample selection and also in our methods of both detection and follow-up, because also our techniques for following up are usually biased. So we concentrate on one sort or the other just because of technical limitations. But because we're aware of those biases, I think it's helpful to be aware of the biases, obviously, but it doesn't mean we can mitigate them, but we can't really do anything really about what we're missing. So I think at the moment, general population statistics of exoplanets in the galaxy, I think we really don't have an idea yet. Yeah. But we are getting there. We do now understand our biases. We know how each of the methods will feed into what sorts of planets we see and what we expect to see. I should say also that Plato will help a lot with this. So Plato is a wide field imager. It's 26 cameras, and that will really get a large sample of newly detected exoplanets in the same vein as TESS and Kepler are also generating thousands of exoplanets each. Ariel isn't so much. Ariel's for following up. So Ariel will give us a good idea of the composition of a lot of different diverse sample of exoplanets, but it won't really fill in the gaps for planets we're already lacking. Like we have a bit of a desert for sub-Neptune type planets at the moment. We're not going to find more of those with Ariel, but with Plato we may do. Okay. Is there ever a risk of double counting exoplanets with the different methods, or are we fairly good at, once we've identified one through one method, we're happy? Or? So double counting, not so much, but certainly in the literature, especially if you go back a decade, you find that orbital parameters of confirmed, in quotes, planets change wildly from one place to the next. So this again, a mission like Ariel, where you have a baseline sample all observed with the same set of instrumentation, is really going to help this sort of thing. We can really help characterize planets, not just their orbital parameters, but actually the composition as well, using a self-consistent set of analysis with the same instrumentation.
So we've got a question in the chat from Graham. Should we be looking for whether exoplanets have a Van Allen belt equivalent before we start denoting them as habitable?
Certainly, I think that when we talk about habitable zone, we're certainly not talking about actually would be a nice place for us to land without a spacesuit, for instance. Yes, I think that looking at the magnetic fields of, I mean, this is more into the stellar physics and the magnetosphere of the star and seeing how that interacts with the planets. I think we don't really understand everything about this in our own solar system. Solar Orbiter at the moment, another great ESA mission, and SMILE, which will launch next year, is going to really look at in detail at our own magnetosphere and really look at these. But still, that's one example of a planet that has this and is habitable. I wouldn't say we should rule anything out if it does or doesn't have it. And I'm afraid it's going to be a while before for exoplanets we can really look in detail at the interaction between an exoplanet and a star. We can certainly start looking at this in stellar environments, but the interaction with the exoplanet is a way off, I think. But yes, certainly it's all things we should consider.
Thank you. In terms of looking of composition of atmospheres, chemistry is not my strength, but presumably the different environment means different compounds might form. Is there a possibility we're forming compounds that we don't see on Earth, and therefore we don't understand the spectral pattern of those compounds? And how do we handle that?
Certainly, we'll see compounds, that we don't see on Earth. I mean, there's a lot of different environments there that are a lot more intense than anything we have in our solar system, even. So we'll see a lot of species which just aren't, especially in the Earth atmosphere. But I think we do have quite a good handle on the processes, and we have quite a good understanding of the chemistry. I wouldn't say I do myself. I'm also not a chemist by background. But I think we do understand a lot of the processes where we can make good models of what atmosphere should be. And then, of course, those will have to be refined as we find observed planets that break all of those models, which is the great joy of seeing Webb data at the moment in all fields, exoplanets and extragalactic as well, where we are really pushing hard to try and break models and see if what we believed before exists. And Webb is very good at this, and Ariel will also help us to really try this as well and test our model.
That's great. We've got a couple more questions in the chat. So Rob is saying, following on from the first question, how are we quantitatively and qualitatively able to distinguish biases? In the absence of observation of smaller, more distant planets, is there a danger we focus our look on for Earth-like planets in the wrong place, since our current observation capability would not be able to see truly Earth-like planets?
Yeah, it's a very good point. I mean, we have got a relatively good handle on our biases, but I think that we do have to be careful that we don't have any unknown biases at the moment. And certainly looking for Earth planets, again, it's not something that Ariel will do. We're not a discovery machine, but Plato are very conscious of trying to unbias their survey, because they are looking for terrestrial Earth-like planets. So they're trying not to go for any particular sort of stellar environment or any particular region. They are trying to be as unbiased as possible to really get a good sample of those planets. And then they're only trying to measure mass, radius, and get the orbital parameters for things that then we can follow up in the future, maybe, or even with Webb.
Yeah. Okay. So it all play together. Another question in the chat is, what data do we expect to gather on differences between early and late migration planets?
So the atmosphere themselves, if it's an early or late migration planet, we'll just have it'll have a different composition. You'll have the embedded chemical composition of the inner or outer area of the primordial disk embedded in it or not, depending on whether it's a late or early migration of a planet. So again, these are things that are modeled by the theorists, and we're hoping to test their models with our observations and then try and break their models and refine everything.
Thank you. Okay. Let's check for hands for that. Looks like that's... Sorry, one more question coming. Yep, okay. Do the current or near-term future satellites have the ability to detect magnetospheres of the exoplanets that we see?
So I think that nothing we have currently can really detect, especially magnetospheres of exoplanets. Even magnetic fields of stars is, I mean, not that new an area of investigation, but it's a relatively new field that we started to be able to look into. So maybe not near future. Unfortunately, funding is being cut for a lot of missions. I don't see anything new popping up there, but hopefully in the future we'll be able to get that link between the stars and their exoplanets in terms of the magnetic environments much clearer. Certainly it's not really something that Webb looks at, and I don't think it's will be something that's on the objectives for like Habitable World Observatory, which is in a couple of decades' time. We're still very much into just direct detection of Earth-like planets with that, rather than looking at more detailed in the environment or magnetosphere of the exoplanet. It's also, I must say, that is not my area of expertise at all. So
that's all right. Thank you. Okay, I think that's all our questions. So just thank you very much to everyone for attending. Big thank you, Tim, for speaking and sharing your work with us today. It's been really interesting to see and hear about the exciting and what is to come, and what it is that we might know in the future.
Thank you very much for the opportunity to talk about Ariel and Webb.